So we know that we can find the stationary points by equating the partial derivatives with respect to x and with respect to y to 0. But now we want to classify them. And in order to classify these points into maxima, minima, and saddle points, we need to study the Taylor expansion of a function of 2 dimensions. And this is very interesting. So let me first refresh you about the Taylor expansion of a one-dimensional function, okay? So in one dimension, you have a function f of x, and to find the Taylor expansion around a point, x0, we wrote that f of x0 plus delta x, meaning that we are in the neighborhood of x0, okay? So delta x is a change with respect to x0. This is approximately equal to the function at x0, that's the first order approximation, or this would be the 0 order approximation, plus the derivative of f with respect to x at x0 times delta x, and this is the first order approximation. So here we are approximating the function with a straight line, plus 1/2 times the second order derivative of f with respect to x times delta x squared, plus ... So we had increasing orders of delta x, yeah, delta x to the power 2, delta x to the power 3, and so on, okay? So the Taylor expansion for a two-dimensional function is quite similar to this, but of course we now have two variables, x and y. So how does it look? We start with a function which is a function of x and y, and I am going to write the first 3 terms explicitly, the same that I did in the one dimension. I will write the 0 order term, the first order term, and the second order term, okay? So this is how these terms look like. The function around the point x0 and y0. So we are writing x as x0 plus delta x, and we are writing y as y0 plus delta y, is approximately equal to the 0th order approximation, f evaluated at x0, y0. This is the 0th order approximation, plus the first order approximation, and this will be the equation of the tangent plane, okay? So the same as the first order approximation in the Taylor expansion, this is the equation of the tangent line. Here, I'm going to write the equation of the tangent plane, which is basically the total differential df, yeah? So it's partial of f with respect to x evaluated at x0. I'm not going to write that because otherwise the expression gets too big, but this partial differential has to be evaluated at x0 and y0 multiplied by delta x, plus the partial differential of f with respect to y evaluated at x0 multiplied by delta y, okay? So this is the first order, let's call it delta f, is the first order approximation, okay? And it's very similar to the total differential, but instead of dx dy being differentials which are a limit when they go to 0, these are actual numbers, scalars, delta x and delta y, okay, which are whatever we want to place here. So this is the first order approximation, and now the second order approximation. So of course, notice how similar this is to the one-dimensional case, yeah? It's just that we added the 2 cases. Now the second order starts also similar. We also have a 1/2 term, but now we have to be careful because we cannot just have this with x and then the same thing with y, because we also have 4 second order partial derivatives with respect to x twice, with respect to y twice, with respect to x and then with respect to y, with respect to y and then with respect to x. We have 4 combinations, and the 4 combinations will be included in the Taylor expression, okay? So this is how the expression looks like. It's the second order partial derivative of f with respect to x squared times delta x squared. So far this is this seems identical. Then we add the same term but for y. Okay, but then we are still missing two terms for the cross variable partial derivatives. Okay, and since they are equal, you know that fxy is equal to fyx. Yeah, they are equal, and therefore we can group them. So we can say times twice the second order partial derivative of f with respect to x and with respect to y times delta x times delta y. Okay, this is the second order correction. And then the Taylor expansion would continue, plus dot dot dot. If you are interested in knowing how it continues, you can go to the PDF notes, and it's written like additional material. This is not going to be in the exam. I will never ask anything above second order. Okay, and also you don't have to remember this expression. This expression you can look it up in the formulas and in the equations. But importantly, this now is the second order approximation. And now, similarly to how the first order approximation is delta f, I came up with this notation. This is only mine, you won't find it in books, but I think it's quite useful to write this as delta and subscript 2 between parentheses, delta f. So this is like the second order approximation, okay? Try to remember that when in the Taylor expansion you included up to second order, you were approximating your function with a x squared type function. So this is the equation of a parabola, and it's the parabola that best approximates your function around the point x0. So here the same thing happens. When you include the 0th, first, and second order Taylor terms into the approximation for a two-dimensional function, you are approximating your function with a parabola in the two-dimensional x and y. So in 3D, this looks like a parabola, it's like a vase. Yeah? So you are approximating your function at that point by using the vase that most approximates the function. Okay. So of course, knowing this second order approximation, we should now be able to classify the stationary point, right? If the parabola is pointing down, then this is a minimum. If the parabola is pointing up, so this is like a mountain, like the top of a mountain, then this is a maximum. And if this is not actually a parabola, but has the shape of a saddle point, then this is a saddle point, right? So the way to classify the stationary points is to use the second order correction, or the second term in the Taylor expansion. So let's summarize what I said earlier. So a stationary point is any point in which the first order correction is equal to 0. Okay, so when this delta f goes to 0, this is a stationary point because both partial derivatives are 0. So that we already knew. But now we can use the second order correction in order to classify the points. So this is how it works. If this second order correction of f is negative in all directions, very important, then this is a local maxima. And actually this is not necessarily two ways. While if the second order correction is positive in all directions, then you are sure that this is a local minimum. Okay? So this equivalence doesn't work the other way around, because sometimes a local maxima has 0 second order corrections, but it has non-zero further order, like third order or fourth order and so on. So sometimes this might be 0 and it's still a local maxima. Okay, so we cannot write the arrows in this direction, but we can write them in this direction. Okay, So maybe what I could add here is that if this is equal to 0 in all directions, then further study required. Okay, but now, even more importantly, if the second order correction of f is positive in some directions, but it is negative in some other directions, then this is what we call a saddle point. Okay, so a saddle point is what we are drawing here, because it looks like the saddle of a horse, right? So you can see that this looks like a local minimum in one direction, but it looks like a local maximum in the other direction. So in total, this is a saddle point. The second order derivative the second order term in the Taylor expansion is positive in some directions and it's negative in some other directions. Okay? So see you in the next video, where I will show you how to know in which case we are.